K2-18B, an exoplanet once hailed as a potential cradle for extraterrestrial life. Recent data from the James Webb Space Telescope has revealed unusual signs: methane, CO2, and most intriguingly, dimethyl sulfide, a compound closely associated with biological activity. But the critical question remains: is this truly evidence of life beyond Earth, or are we witnessing a profound scientific misunderstanding? In this video, we're going to cut through the noise. No hype, no speculation, just the facts. We'll clarify the ongoing debates, dive deep into the research, and dissect what's real and what's overblown. No clickbait, no assumptions, just science. When it comes to the search for life beyond Earth, few stories encapsulate as much curiosity, controversy, and wonder as the case of K2-18B, an exoplanet orbiting a red dwarf, approximately 120 light-years away. Once an obscure name buried in NASA's catalog, K2-18B stepped into the spotlight after spectral analysis revealed unusual signals in its atmosphere. Specifically, a research team in the UK published preliminary findings of a compound known as dimethyl sulfide, or DMS, a molecule on Earth closely associated with phytoplankton and marine bacteria. If DMS truly exists in the atmosphere of an exoplanet, it would be one of the strongest biosignatures ever detected beyond the solar system. But digging even one layer deeper reveals that this is not simply a story of life or no life. It is a case study in how science truly operates through skepticism, self-correction, and constant challenge of its own assertions. First, we must understand why DMS commands so much attention. On Earth, DMS is a sulfur-containing compound primarily produced by ocean-dwelling life forms. It plays a role in cloud formation, climate regulation, and serves as an indicator of a thriving marine biosphere. Its presence in Earth's atmosphere is considered an indirect marker of life, which makes the idea of finding a similar signal on an exoplanet nearly irresistible. But that allure is a double-edged sword, because when expectations rise too high, the potential for disappointment becomes equally great. Data from the James Webb Space Telescope, JWST, indicated that in the absorption spectrum of K2-18B, there were faint signals compatible with carbon-based molecules, potentially including DMS. But the reliability very low. In fact, the original study explicitly stated that the signal did not exceed the statistical threshold required for scientific confirmation, calling it a tentative, inconclusive result. The controversy, however, wasn't sparked by the paper, but by the press release that accompanied it. In an effort to communicate the discovery to the public, the research team used much stronger language: clear signal, significant match, and high likelihood of DMS. For the average reader, these phrases imply a confirmed finding, something virtually irrefutable. Naturally, this triggered intense backlash from the broader scientific community. Many saw this as a classic example of science communication being driven more by publicity than by cautious fidelity to incomplete truth. Leading the critical response were seasoned astronomers who reanalyzed the original data. One such figure, Dr. Jake Taylor, used a different statistical model from the original team. His result: not only did it fail to confirm the presence of DMS, it ruled it out entirely. When the spectral analysis was no longer biased toward fitting DMS, the signal vanished. This raised a difficult question. Was the signal ever real, or merely the artifact of a data filter designed to find what it was looking for? It didn't stop there. Another independent study, led by Professor Louise Wellbanks, demonstrated that hundreds of other organic molecules could produce signals indistinguishable from DMS in spectral data. The conclusion: assuming that signal is DMS is not only unfounded, but it overlooks dozens of equally plausible alternatives. The issue becomes even more complex when we learn that DMS, once considered a biological fingerprint, has been found in lifeless places. One example is Comet 67P, explored by the Rosetta spacecraft in 2006. Scientists found DMS in the comet's surrounding gases, and clearly, no one believes comets harbor marine bacteria. Similarly, giant molecular clouds near the galactic center, chaotic star-forming regions, also contain notable concentrations of DMS. Certain inorganic reactions, especially involving methanol, can produce DMS under extreme conditions, no biology required. These pathways have been confirmed both theoretically and in laboratory settings. So if DMS can naturally form throughout the galaxy, what does its presence on K2-18B really tell us about life? In defense of their hypothesis, the original research team expanded their analysis this time, comparing the absorption spectra of K2-18B with over 650 different molecules. Their conclusion DMS still remained the best fitting candidate. Other molecules such as methyl acrylonitrile and dimethyl sulfide, both associated with biological or microbial processes on Earth, were also considered. Still, the scientific community's response remained unchanged. This was still just a reanalysis of old data, and the findings still failed to meet the 5 sigma statistical threshold, the gold standard in physics and astronomy for claiming a discovery. Moreover, these complex molecules could just as easily be the result of prebiotic or abiotic chemistry, especially in the harsh atmospheres of gas giants like K2-18B. Another major problem, stellar contamination of spectral signals. Stars, especially red dwarfs, are anything but stable. They frequently release solar flares, star spots, and brighten or dim rapidly. K2-18, the host star of K2-18B, is no exception. These stellar phenomena can distort or mask the planetary signal, making it extremely difficult to identify atmospheric components accurately. A single star spot aligned with the planet's orbit can mimic the signal of an organic molecule. This isn't speculation, it's a known and accepted challenge in exoplanet astronomy. Determining the atmospheric composition of a planet orbiting a red dwarf remains one of the hardest problems in the field today. Notably, Professor Sarah Seeger, one of the most respected astronomers in exoplanet science and a past contributor to K2-18B research, has publicly warned about the limitations of JWST. According to her, the telescope's transmission spectroscopy, while sophisticated, is highly vulnerable to stellar and cosmic background noise. In a recent paper, she emphasized that our current tools may never be sufficient to confirm life, even indirectly, through atmospheric signals alone. This isn't a rejection of scientific progress, but rather a sobering reminder. In astronomy, dreams must always be tempered by extreme caution. Pulling all this together, one conclusion becomes clear. There is no strong evidence right now to confirm life on K2-18B. DMS may be present, but it is not proof of life. Its detection in lifeless environments elsewhere has weakened the original argument. The presence of other complex molecules is interesting, but still pure possibility, not confirmation. The public portrayal of these tentative findings as breakthroughs has inadvertently fueled false expectations, something rigorous science always strives to avoid. And yet the most valuable outcome of this story may not be the answer to whether life exists, but rather the process of debate itself. Thanks to scientific pushback, we are forced to refine our methods. Thanks to reasonable doubt, we are protected from false conclusions. Thanks to revealed limitations, we are motivated to build the next generation of instruments. And thanks to differences in interpretation, we learn to discipline our beliefs when facing prematurely packaged information. Science is not a place for quick conclusions. It is a domain where every claim must pass through layers of verification, scrutiny, and independent confirmation. In a world where headlines spread in seconds, patience becomes the key to accuracy. K2-18B, though it may not yet yield proof of life, remains a valuable lesson in how we should approach cosmic signals, not with blind faith, but with informed skepticism. And that is the true beauty of science. not in declarations, but in the journey toward truth. Even when it is slow, difficult, or challenges our deepest hopes, the universe has a way of making us hope, then challenging us to question that very hope. K2-18B might be a turning point, or simply a reminder that the search for life beyond Earth is never easy. If you found this video helpful, don't forget to like, subscribe, and share, so more people can understand the science the right way. And drop a comment below. What do you think about K2-18B? We'll be back with even stranger stories from this vast cosmos. See you in the next video.